Good day to all of you. Recall that we were discussing how to regulate multiple output power supplies. Out of the multiple outputs, one of the output is fed back, and that will be the controlled output. The remaining outputs, which are uncontrolled, needs to be locally regulated, and in this respect we discussed few measures. And the following were some of the measures that we discussed in regulating multiple output power supplies or DC to DC converters. So, the first one which we discussed was based on the linear regulator. Then we discussed non-isolated, locally controlled, switched mode DC-DC converters in place of the linear regulators. We discussed the coupled integrator, the coupled inductor method, and then we were discussing the process of trying to understand the magnetic amplifier method. We shall try to continue this discussion and complete this discussion in this class, and then take up the next topic. So, if we take the case of the magnetic amplifier based method, we discussed that we will be, I will just draw here now only one winding. It is assumed that there may be other windings. There is one saturable inductor and we have and then the regular buck converter, which is present in other forward winding converters. It may also be flyback winding, a flyback based output. Now, at this point we are trying to interpose a current source which is derived from the output and is going to direct current in this direction as shown. Now, let us look at this component, the saturable inductor component. The voltage across that, this is called Ls, the current through that, and of course the flux in it. And then as a consequence, let us look at the voltage at this point. We will call this point as C, voltage at C, and then the voltage V naught at the output. Let us have a look at these parameters of the circuit, these points of the circuit where we can study the waveforms and try to understand the this particular magnetic amplifier circuit. And after we do that, let us look at how we are going to incorporate this portion of the current controlled current source here in the circuit. So, we shall plot the waveforms here. Okay. So, one by one, let us not forget the dot polarities as a forward converter. Now, when the switch here is on, this dot is positive and this is positive. Okay. And initially the inductance acts as an impedance on open circuit and does not allow that voltage to appear at this point in order to forward bias this diode or appear at this point till that gets saturated. So, let us look at the current and the voltage wave shape of the inductor Ls. So, let us divide it into 4 parts, the time scale into 4 parts. Where this is dTs 1 minus dTs, dTs 1 minus dTs. These are the times, and during, if you say this is Q, this is V n, this during this time Q is on, during this time Q is off, Q on, Q off. And now, the moment Q goes on, the voltage Vs, let us say this is 1:n. So, the voltage Vs would be n times V in with the dot end positive. Now, this diode is freewheeling This diode is freewheeling because of the inductance and output inductor stored energy. So, this point is ground potential for this diode, and this voltage is positive at the dot end. So, there is a current that is going to flow through. This would be positive side of the anode of the diode. This diode is forward biased, and you can have a current flow through this. As long as the current through this loop is lesser than the current of this loop, this diode will conduct. So, let us assume that the current through this is lesser than the output load current, which means this inductor current ILS is increasing. So, let us say ILS is increasing like that. At the same time, let us say the flux is also having the same pattern, increasing along with the current, only the rates are different. VLS is equal to LLS DILS by dt, which is equal to NLS, the turns of the winding, d phi LS by dt. So, if you look at these two equations, the rate for the current is VLS by LLS, and the rate for the flux is VLS by NLS. So, these two rates are the ones which dictate the slope. VLS by LLS dictates the slope of ILS, and VLS by NLS dictates the slope of the flux within the core. However, as in the linear region, LLS is constant, VLS is a constant, it is a linear slope, VLS is a constant, and NLS is a constant, that is also a linear slope. Now, let us say that the saturation limit, the flux saturation limit is at that point. So, which means that flux flattens out. The voltage across the inductor becomes 0. The moment the voltage across the inductor becomes 0, this diode, the voltage through this diode will appear at Vc and reverse biases this diode, and this diode switches off, and the entire load inductor current commutates as the input current. So, what will flow through ILS? ILS, which is now acting as a shorted, which is acting like a short circuit, will pass the current which was flowing through the output inductor as is. Now, during that time the voltage V naught, the voltage VLS, which was positive and which was a positive value. Let us not clutter it up, let me just up to this time, and at this point of time it goes to 0 because this diode conducts. So, here the LLS, the saturable inductor, is acting as an impedance. During this time the flux has saturated, inductor, the saturable inductor is no longer acting as an inductor, but as a plain wire. The voltage comes up to this point Vc, turns off this diode. So, the voltage across the inductor is, saturable inductor is 0. And if you look at the voltage across, if you look at the voltage Vc across this diode, we see when the diode was freewheeling up to this point, let us say it is an ideal diode, the voltage Vc was 0, and then once the inductor saturates, the entire secondary voltage NV in appears at this point. Now, this transistor Q is turned off. The moment transistor Q is turned off, there is a reversal of polarity in the primary, and therefore, a reversal of polarity in the secondary. The primary, there is a demagnetizing winding which tries to take care of the flux in the primary transformer. So, now during the time when this is off, the voltage across this inductance should be negative in order to achieve volt second balance. Now, how is that brought about? Let us say there is a current which is flowing from this current source. How we get that current source, we will see that later. Let us say that current flows through like this, through the inductor. So, when the current flows through the inductor in this fashion, look at this equation. When the current flow is in the opposite direction, meaning a negative current, therefore, a negative slope, the voltage across the inductor becomes negative. Now, let me draw the current through the inductor starts flowing in this direction. Let us say we give a linear current increase. Now, based on this slope, linear current increase up to some point, let us say. Let us say the current goes in this fashion, and therefore, as a result, the flux also goes down by VLS by NLS. Now, let us say it goes and settles down at that point. Now, because the flux and the current are negative, the rates are negative, you have a voltage which is negative from the Faraday's equation. Let us draw that. So, this goes negative. Now, if the current rates are such that, this negative value is less than n times V in, with the dot end negative and the non-dot end positive, then the remaining voltage will appear across this diode as reverse bias, because this is conducting and this diode is turned off. Therefore, you can be assured that all the current flows only in this direction. So, now during the time when the transistor was off, this is what was happening within the saturable inductor. What is the current during this time? ILS looks like there is a jump from here to here, but let us look at this later. Now, when at the onset of the next period, the voltage again becomes positive, because the moment Q is turned on, the dot end becomes positive, the dot end on the secondary side becomes positive, NV in, and that appears across the inductor. The inductor has, from the saturation state, has reached a non-saturating state, because the flux has decreased, because we have provided a negative current. And it would stay there till a point where the flux starts rising, and at some point again it reaches the saturating state. And like before, the current is also increasing, at more or less the same, this is increasing at more or less the same slope or same rate as this, because the slope of the current is determined by VLS by LLS, which was same as before, and the slope of the flux is determined by VLS by NLS, which is the same as before. However, the starting point can be different for the flux. And how can the starting point be different? By giving different negative slope rates of the current by adjusting the value of the current source, the current which is driven during the off condition, the flux can be brought down to different values, either to 0 or bit less than 0 or still up. And as a result, the starting point for the flux can be different, and when it goes at the same rate, it will go and intersect at different time points in the dts on time, like this. So, at the point when it intersects the saturation flux value, the voltage becomes 0. The moment the voltage becomes 0, the whole secondary voltage gets passed on to the point Vc, and the Vc would look like this. And the second, when the Q is again switched off, again the voltage here would go positive or negative. Depending upon the current flowing through LLS, but we are always going to allow the current flow in only one direction, which is in the opposite direction to what was flowing when the transistor Q was on, and therefore, the voltage will always be negative as compared to this in order to maintain volt seconds balance. So, by controlling the rate, of current that is going to flow in the saturable inductor in the reverse direction, you can control the amount of voltage that is appearing across the negative voltage that appears across that inductor, and as a result control the flux rate within the core, and you can make it at the time, at the end of the period, you can make it intersect or come down to or reset to a value either 0, negative or positive. So that for the next period, new period, the starting points can be different, and as a result you notice here different starting point of the flux will give you different pulse width. You see a different starting point for the flux at this point, you will get a different smaller pulse width. So, if the starting point of the flux is higher up in the y axis, you would get a larger pulse width. If the starting point is lower down on the y axis, negative and lower towards the minus phi sat, then the pulse width which appears at Vc is smaller. So, this is some kind of a pulse width modulation which is happening locally by means of injecting different current rates during the off time of Q. So, this is the essential principle. Now, what is happening to ILS current during these times? It will just take the same value of the inductor that was flowing through and which gets commutated from this diode. So, during the times when Vc is high, the inductor current commutes to ILS. So, understand this better. Let us clear some portion of the screen here. And let us extend. So, we know that so let me extend this axis a bit. This T now consider I L. Now, I L, I am going to put that in red color. So, the current through the inductor is going to flow in this fashion. So, as far as the inductor is concerned, this portion is the time the inductor will consider it as on, and this portion of the time the inductor will consider as off time, and on time, off time. So, the inductor current under steady state, you would see that it is going this fashion, goes at, because this entire period, this entire time width is the freewheeling time. This entire time is freewheeling time. As can be seen here, during this time, this diode is always conducting, and then the inductor is freewheeling for the entire portion. Only during this time you have the non-freewheeling time when the energy is put into the inductor. So on, and it would be in this fashion. So, during this time, the inductor current, the inductor current will become the current for ILS. So, ILS will take on a shape like this. Let us say it goes like this. I will erase this portion. So, that would be the shape of the inductor, would be the shape of the current ILS through the saturating inductor. So, from this we see that the voltage at this point is a kind of a pulse width modulated voltage, where the pulse width can be adjusted by the current flow which is made to flow through the saturable inductor. and the output voltage is nothing but average of the voltage. Just like buck converter operation, the average of the voltage at this point is the voltage which occurs here, which is nothing but D into Vc. So, the average is given in this fashion, and this is, if this you consider as the on time T on now, and this is considered as the off time T off, then V naught will be equal to T on by T on plus T off into N V N. Now, that would be the voltage at the output. Remember that by controlling the rate of flow here, we are able to control the on time. So, this is controllable. So, like a variable duty cycle function, and therefore, the output can be regulated by controlling this T on, which means by controlling this current rate. So, that is precisely that what we will be doing. Controlling this current will control basically the T on of the local switching, which will control the output voltage. So, now coming to a more operable circuit, let us draw the circuit. Now that we have understood the principle, we have a forward converter, and we have the saturable inductor and followed by the regular buck topology of the forward converter. In this fashion, this is the saturable inductor, this is Vn, and we have the dot polarities like this. Now, let me draw the injected current in a different color. Now, at this point, let us inject current in this fashion. Now, let us draw the current from the output in this fashion. A resistor, and let us say you have a PNP transistor, which acts as a switch, not a switch, a linear resistance. So, what happens here is that based on the gate drive here, the transistor starts getting into different operating points along its load line and tries to draw that current and pass that current on to this portion of the circuit. Now, how do we give this gate drive. This gate drive should be such that the bias current, the base current biases this transistor at an appropriate operating point such that just that correct amount of current is flowing through the inductor in the negative direction to reset this core to an appropriate flux level for starting in the next cycle when this switch is on. So, to do that, let us have a reference. Now, what should this reference represent? It should represent V naught, which is this. So, let us say this is the set reference of V naught, and since this V naught, this is V naught sense, this is minus, this is plus. Now, what happens here? Now, let us say that the V naught has decreased. So, the moment V naught has decreased, this has become lesser, this will become more. So, once this has increased, this will start getting biased towards cutoff, and as this starts getting biased towards cutoff, the current flow here reduces. So, once the current flow here reduces, the resetting action on this inductor is reduced and the flux reduces at a slower rate. And therefore, by the time the end of the period comes, the flux would have reset to a higher value than before. And because it has reset to a higher value, as you saw previously, as the flux resets higher up in the y axis, the pulse width increases. Once the pulse width increases, the output voltage will increase. So, that is the control action that is happening here. So, if V naught decreases, V naught sense decreases, and let me call this one as E error, error increases, and let us say the current IQ, the IQ current decreases because the PNP is now biased more towards cutoff, and as a result pulse VC width, VC is this one, VC width increases and therefore V naught increases. So, this tries to bring this back to the original condition. Likewise, when V naught increases, V naught sense increases, error decreases, IQ increases, VC width decreases and V naught is decreased and brought back to the original state. So, this is the control action that is happening. Now, let us say we can try to implement this with an OpAmp. So, let me make some space here. Let me try to implement this portion with an OpAmp. put a resistance and OpAmp minus plus, and we could have a reference with a Zener. In this fashion. So I am labeling it such that notice that this point is same as this point, and likewise this point is same as this point. The OpAmp will also be driven likewise from the output, so that it is self-contained, and the OpAmp so this is inverting OpAmp. There is an inverting OpAmp which is powered from the V0 plus and V0 ground. This is V0 plus, V0 ground. The positive input of the OpAmp is given from a Zener. This is V0 reference that we are trying to give. So, from the V0 output and ground unregulated, which ultimately gets regulated, you can generate a reference using a Zener, which gives more precise regulation than what you achieve at the output, and then that is given through a pot, and a value is set here. That positive point of the OpAmp, that will be the reference point. Then to the negative point, it is coming from V0 itself. So, the V0 a line is taken from here, that will be the V0 sense. V0 sense, and through the non-inverting amplifier appears here. So, if V0 sense decreases, this output would increase, and because this output increases, this transistor, which is a PNP transistor, gets biased towards the more towards the cutoff, and as a result, what is drawn from the output is a lesser current which is flowing through this, and because the lesser current, the resetting is lesser, and therefore, in the next cycle Vc has a higher pulse width, and therefore, V0 is brought back to its original state. So, this would be the complete circuit for a possible magnetic amplifier technique of regulation in the local loop. So, the regulation is in the local loop. This duty cycle is controlled based on the controlled winding loop. Okay. Whatever that happens, this inductor is acting as the control for this particular output through this means. So, now that we have studied how various means of regulating the outputs of a multi-output DC-DC converter, we shall look at some applications where you may not want to regulate the output voltage, but you probably may want to regulate the current, or you may want to regulate both the current and the voltage. So, how do we go about doing current control? So, the next topic that I want to take up and introduce you to is the issue of current control in DC-DC converters. So, you may ask where we may use this current control. Isn't it normal that we have only voltage control, and shouldn't voltage control be sufficient? However, you will see many applications where current control is essential and necessary also. Let us say, for example, you have two power supplies. You have power supply 1 DC-DC converter, and that is supplying a load. This is our load V naught. Now, suppose let us say this particular power supply is not fully able to supply this load power. Load power can vary. Now, let us say this power supply has a maximum limit of, let us say, 500 watts, and let us say that you need 750 watts here. The load can swing from 0 to 750 watts. So, up to 500 watts, when the load here swings up to 500 watts, the variable load, this DC-DC converter is sufficient and it can bear the load. However, the moment this load increases beyond 750 watts, this DC-DC converter will not be able to handle it. Okay, one method is that you design a DC-DC converter which is rated for 750 watts or higher than 750 watts. But let us say in our inventory, we have only DC-DC converters designed and made for only 500 watts. Is it possible to solve the problem with having a smaller wattage DC-DC converter in the inventory and catering to higher wattage loads? Now, that is where one possibility is to have another same identical DC-DC converter, and that is also rated for 500 watts nameplate, and let us say it is drawing from the same battery or another battery. For the input, and the output is paralleled like this. So, if a load is, let us say, some 500 watts, will it draw, if the load here at any given moment or given point of time, let us say, I will put it as 600 watts. So, will it draw 300 watts from here and 300 watts from here automatically? Is it possible? If it is voltage controlled, what would happen is most likely this will blow, this will also blow. Why? It is like now connecting one voltage source in parallel with another voltage source in parallel with the load, R load. However, observe the issue, you cannot connect two voltage sources in parallel, because there will always be mismatch of voltages and each voltage source will try to dominate, and as a result there will be circulating currents within this loop, and these circulating currents can be very high because the impedance in this loop is very low, ideally 0, and even a very small mismatch in voltage can cause hundreds of amps to flow and therefore blow up both this and this sources. It can blow up both the sources, or it can blow up one source and a load which is exceeding the rating of the other source can blow up the other source. Whatever sequence, these sources will go bad. So, under such condition, we need to have a control method where instead of having a controlled voltage source, we have a controlled current source. So, you have a controlled current source and controlled current sources can be connected in parallel, because the output current of each of these sources are dynamically controlled. So, even if now let us say now this is a 500 watt source, this is a 500 watt controlled current source, and you are demanding from the load 600 watts, then you can set to draw 300 watts from this source and 300 watts from this source, or you can make it to happen with 400 watts from this source or 200 watts from this source. So, with current control, this sort of a strategy is possible and very advantageous when we want to use it for power source for loads which has ratings, power ratings much higher than individual current source. And this is what we will try to explore in the next class. Thank you for now.